This is the second part of our acid-base equilibria. This part will consider protons in water and pH and pOH functions. Acids and bases are defined in the terms of transfer of hydrogen ions H+. Note that these hydrogen ions are often referred to simply as protons, since that subatomic particle is the only component of cations derived from most abundant hydrogen isotope. Protons are very small, 100,000 times smaller than any atom. We can observe free protons in vacuum, but never in liquid or solid, or even in gas at normal pressure. Protons in water are always located as a lone electron pair of water molecule, forming hydronium ion, shown on this figure. All three hydrogen atoms in this ion are exactly identical. Nevertheless, we often say and write proton instead of hydronium or oxonium ion. Doing that, we must always remember that the proton is not free particle, but it is bound to a solvent molecule, water in this case. Hydronium ion interacts with neighboring water molecules through very strong hydrogen bonds, forming more complex aggregates, such as so-called eigenion. In center there is hydronium and three neighboring water molecules attached by hydrogen bonds. Additional, much weaker hydrogen bonding with the next layer of neighboring water molecules make even larger assembly. So, when should we stop? The most common approach is to write H+ and say proton. We must always remember this is dramatic simplification of what actually happens in water or any other solvent. Proton never stays alone on its own. It always sits at some molecule. Just a reminder, acid-base properties of water. Water dissociates itself on H+ and OH-, that we name autoionization of water. In this scheme, one water molecule serves as acid, another, this similar water molecule, serves as base, making H3O+ hydronium, and OH- hydroxide, which is conjugate base to water molecule. Liquid water undergoes this autoionization to very slight extent. At room temperature, approximately 2 out of every billion water molecules are ionized. The extent of water ionization process is reflected by the value of its equilibrium constant, so-called ion product constant of water, Kw. So for reaction, H2O makes H+ plus OH-. Equilibrium constant should be, drawing the line what's above, concentration of H+ multiplied by concentration OH-. Now, we must divide on concentration of our reagents, which is water. But we are talking about pure water, so molar fraction of water in water is 1. We can skip that. Because of that, we do not have ratio, we have product, H+ multiplied by OH-. This process is endothermic, so the extent of ionization and resulting concentration of hydronium ion and hydroxide ion increase with temperature. we can look at this table. At room temperature, again, we have 10 to the negative 14. With freezing temperature, we have practically 10 to the negative 15 at 0 Celsius. Next to boiling point of water, around 80 degrees, it's becoming 10 to the negative 13 and quickly reaches 10 to the negative 12, slightly above 100 degrees. Why we are interested in such high temperature? It's visible that acidity of water increases with temperature, so water at high temperature is becoming more aggressive and can corrode, for example, pipes of power plants or other sensitive equipment that should work for tens of years without corrosion. So electric power plant people are very interested in that. Nevertheless, in the lab, we are interested only at room temperature. So 10 to the negative 14 is a good approximation for this class, for any purpose. Common way of expressing quantities that can span many orders of magnitude is to use log scale. Such scale is very popular for chemical concentration and equilibrium constant. It is named so-called P function, defined as negative log of concentration of X. For species X, negative log of concentration of X is Px. So in this case, pH of solution is defined as negative decimal log of H plus concentration. pH minus log H plus. Why minus? Because most of concentrations are smaller than 1, so log will be negative number. If log is negative, negative log will be positive number, which is more convenient. You can come back to concentration. You rearrange this equation and have H plus molarity equals 10 power minus pH. We can go back and forth as many times as we want. Likewise, hydroxide ion molarity may be expressed as P function POH. POH is negative decimal log of hydroxide molarity. Same way as with H plus, molarity of OH minus is 10 power minus POH. Now, the relation between these two concentrations, expressed as P function, are easily derived from Kw expression. So Kw is H plus molarity multiplied by OH minus molarity. Now, if we are using the same P function for constant, so pKw is negative decimal log of Kw, then pKw is equal pH plus pOH. Now, value of pKw is 1 to 10 to the negative 14. So, pKw is 14. And 14 equal to pH plus pOH. That means anytime you know pOH of solution, you can calculate pH. Anytime you know pH, you can calculate pOH from this very simple equation. Okay, quickly, what's concentration of hydroxide ion in solution of hydrochloric acid, whose hydrogen ion concentration is 0.13 molar? Now Kw is 110 to the negative 14, H plus is 0.13. Hydroxide is Kw divided by concentration of H plus. And we have our result. Now, hydronium ion molarity in pure water or any neutral solution is 10 to the negative 7. Why it is so? Because H plus equals to OH minus, then H plus should be 10 to the negative 7 to make the product 10 to the negative 14. That means pH and pOH of a neutral solution are identical and at room temperature are pH 7 and pOH 7. So for neutral, pH is 7. For acidic, H plus is more than OH minus. That means H plus is more than 110 to the negative 7 and pH is less than 7. Smaller pH, larger acidity. Now for basic solution, concentration of hydroxide is larger than concentration of H plus. H plus is smaller than 10 to the negative 7 and pH is larger than 7. A larger pH, more basic is that solution.